Okay, this is our last lecture on gravity using Newton's laws. And then everything else we're going to do with gravity will be modern physics. So we have Newton's law of universal gravitation. We've been using it to find forces between two objects. Usually one has a very large mass, and we can find the gravitational force. So in the homework problems, a lot of the problems will ask, well, actually, a couple of the problems will ask you to find gravitational forces, and that's what you're doing. There's another type of problem, and they will ask you to find, the book uses the word surface gravity. It's a little different from what I'm used to. Surface gravity is equal to the acceleration due to gravity. So on Earth, that number was discovered by Galileo, and that number was about, or is about, 9.8 meters per second squared. So that's the surface gravity of Earth, or the acceleration due to gravity. But we know that that number is different on different planets or different places in the universe. So for instance, on the moon, because the moon has a smaller mass and a smaller radius, the surface gravity is something like 1.6. So if people feel like bouncing on the moon, we say, right? Because their acceleration due to gravity is smaller. So if you jump up, you're going to accelerate back down at a much slower rate. So you can find that acceleration due to gravity from this equation. So I'm going to do an example on the Earth. So let's say that this is the Earth, and you are standing on the surface of the Earth. So this is you. And if you're standing on the surface of the Earth, this is a bad picture, this is the center. You're the radius of the Earth away from its center, right? And so the gravitational force between you and the Earth is equal to big G times the mass of you times the mass of the Earth divided by the radius of the Earth squared. So using Newton's universal law of gravitation, that is what the gravitational force on you would be. But I was using a different equation all the way, many problems up until like this week. And so when I was saying force of gravity on you, like when we were drawing free body diagrams, if this is you, the force of gravity on you, I kept calling mg, right? I'd say if you're on Earth, you've got mg down, you've got a normal force up, and this is the force of gravity on you. So if I was not lying, and I wasn't, then that means that the force of gravity written this way must be equal to the force of gravity written the other way, right? They have to be the same if we're using the same words to refer to that force. So that would be equal to the mass of u times g. And when I was using mg, I always put 9.8 in for g, right, in my force problems. So if we look at this, if we say g times the mass of u times the mass of Earth divided by the radius of Earth squared is equal to the mass of u times little g, the mass of u cancels. It's on both sides of the equation. And so what I end up with is little g, which again is 9.8 for the Earth, is equal to big G times the mass of the Earth divided by the radius of the Earth squared. This can be generalized, so to a second equation. So this first equation is the equation for force. If a problem asks us to find force, this is what we use. The second equation is when we were asked to find surface gravity, or the acceleration due to gravity. That acceleration is equal to big G times the mass, I'll put P, the mass of the planet, but it might be a star as well. So times the mass of the planet or star divided by the radius of the planet or star squared. So for things other than Earth, we can put these values in and find their acceleration due to gravity. Actually, using this equation is one way to find the mass of Earth. So one of the practice problems on the PowerPoint, and I'll wrap up with that one, said if we know that the radius of the Earth is 6.86 times 10 to the 6 meters, which we knew this value before we knew the mass of the Earth, just because people had circumnavigated the globe, so they had a general idea of what it was. And if we know G on Earth is 9.8, which we knew from Galileo, then find the mass of the Earth. So if I solve this equation for mass of the Earth, I could say the radius of the Earth squared times little g is equal to big G times the mass of the Earth. I divide both sides by big G, and then I solve for the mass of the Earth. It ends up being about 5.98 times 10 to the 24 kilograms when I put those values in. But that's one way people came up with the mass of the Earth. The other interesting thing that comes out of this is you see, or if we go over here to the generalized equation, the acceleration due to gravity depends on the size of the planet in question, but not the object that's accelerating. So then we were looking at you, right? Your mass canceled out. And this proves again what Galileo said, that all objects, so this would be true on other planets and stars as well, all objects fall at the same rate if we ignore air resistance, because they're all accelerated by gravity, and to find that acceleration, it depends only on the mass and the size of the planet or star in question, not at all on the mass of the object that's actually falling. So, in a nutshell, this is how we find surface gravity. Now, if this number becomes huge, so big that even traveling at the speed of light, let's say, you can't escape it, then we have something called a black hole. When we talk about modern physics and Einstein's picture of gravity, we will talk more about that idea of a black hole. So I'll make, for the end of the week, you'll have some demo videos with gravity, and we will get into that idea. But for this chapter 5 homework set number 2, you're, for every single problem, either using this equation to find force, or you are using this equation to find acceleration due to gravity.